So today what I'm going to talk about is particle position, velocity, and acceleration. This is one of the first sections of the particle kinematics course or chapter, and it gives the groundwork and the foundation for what we talk about in the rest of the course. In particular, what I'd like to do in this lecture, which is probably the first lecture that will be released to you, is define what the goals of the course are and to look at the fundamentals of particle position, velocity, and acceleration. So if we start with that, we kind of have to give you a global sense of where this is all going to go. What are we going to learn in MIE 100? And it's really mechanics, study of how bodies move and what are the forces that cause this motion. And up till now, in the Civ 100 class, you've looked at bodies in equilibrium, so some force is equal to 0. And you saw that even though that looks like a relatively straightforward equation, there are a lot of complications associated with that in terms of what you're doing and what you're looking at. Dynamics is dealing with two aspects. Kinematics, which are the geometric aspects of the motion, and in a really simple way, I'm going to say, look, it's the position, velocity, and acceleration of a particle. When we deal with chapter 16, we go from particles to rigid bodies, and they're going to deal with rotation as an additional complication. Then when we go through the rest of the book, chapter 13, 14, 15 correspond to 17, 18, and 19. And all of these are Newton's second law, sum of forces equals mass times acceleration. However, 13, 17 deal with kinetics, 14, 18 deal with work energy, and that's sum of forces equals mv dv dx. And chapter 15, 19 is momentum, sum of forces equals m dv dt. And it gets more complex in terms of 17, 18, and 19 in terms of the addition of moment equations. Finally, we return to particles to a large extent in chapter 22, which is the vibrations. And the equation we look at is sum of forces equals mass x double dot, which is the second derivative of position with respect to time. So let's start out by trying to define things for a rectilinear displacement, and that's single line motion, and we're going to do that for particle position, velocity, and acceleration. So I'm going to define an axis. The axis goes left to right, and you see the thick blue arrow pointing in the direction. That's your x-axis. The origin is where the intersection point is, and I put a point to tell you where that is. And that's where the particle is at that instant. So it's some distance away, and I can define that along the x-axis using the origin as the reference position. And so I can do that as a scalar magnitude. For one-dimensional motion, this is a reasonable way to do it because you have motion that is either going to be positive x or negative x. And so it corresponds very well to the vector, which is going to be denoted by this arrow on top of the variable. So I will define that as r. So r is defined from the origin to the particle also. Displacement is sort of a mid-step in terms of the analysis. We don't do very much with it later, but it goes and sort of describes where the particle has moved from position 1 to position 2, so s to s prime or r to r prime. The difference between the two positions is delta s or delta r. And so you can define that either as delta s equals s prime minus s or delta r equals r prime minus r. Well, displacement on its own is not very interesting. Displacement over some time is. So, you know, if, for example, you're traveling a kilometer and it takes you an hour, that's a kilometer an hour. That's kind of interesting, but not terribly exciting. If I could do that same kilometer in about 5 seconds, you might realize that there's a significant change in how things happened. So again, I have delta r or this s sub t that tells me what the displacement of the particle is. So if it occurs over some time delta t, we can say, okay, that's the velocity, and the velocity average is just delta r over delta t. For the instantaneous velocity, as I bring down the velocity down to, or the time down to delta t less than 0, I have delta r over delta t, or at the limit, dr dt. So I have an instantaneous velocity term. And the magnitude of the velocity is the speed. And so that's that displacement over time. It is going to be the total displacement. So if the particle moves back and forth, total displacement is going to be larger, but the total magnitude of that displacement is going to be a positive number, and it's always positive. So velocity is in that direction, and that sort of gives you a vector. Acceleration is the last term. And so again, you have a particle and it's sort of there. You have acceleration, which is delta v over delta t, which is the average acceleration over some long period of time. And as you bring it down to a short period of time, you can say, or infinitesimal delta t, acceleration is equal to dv dt. So as it moves from position 1 to position 2, that's the difference between v and v prime. And in this case, you can see that the two arrows are longer. The v prime arrow is longer, and you can see that it is it's going to be a positive acceleration. It goes from smaller velocity to a higher velocity as it goes from v to v prime. However, if I switch it around so that v is at a higher velocity and v prime is at a lower velocity, that's a negative acceleration or a deceleration. And so the other thing to remember, and this is what we do sometimes, is, well, we can say, well, v is equal to dr dt, and I can put the terms into, or substitute my velocity expression, which I have just above. And that velocity expression tells me that I have a dr dt there, and I can make that substitution and get that as a second derivative of position with respect to time. Now, that also allows me to make that substitution for dt. I could say dt is equal to ds over v, sort of do some manipulation and play a little game with this. And remember that this is one-dimensional motion, so my vectors and scalars sort of line up. Acceleration ds is equal to v dv, or acceleration equals v dv ds. So great, I have three equations that I can use for motion: velocity, position, and two expressions for velocity, one expression for position. And the fact is that two of them are independent. So I can't use my acceleration equals dv dt and my acceleration is equal to v dv ds, independent of one another. It's the same thing. The other case, and one of great interest to us, is constant velocity, and constant velocity is velocity, or constant acceleration. So velocity is a function of time, so it increases, but the acceleration is constant. And then you can immediately think of a case like gravity. So acceleration constant equals dv dt. I can integrate it from the beginning to the end, v naught to vf dv, 0 to t, beginning time to end time, and the constant acceleration is there. So I have an expression there that allows me to sort of work immediately with all of these terms. But remember that this often is going to be g. And we'll see that when we look at the particle projectile motion. So v final equals v naught plus act. Position is a function of time, v equals ds dt, do the integral. And all I'm doing here is substituting in this expression into v. So my final position is equal to my initial position plus initial velocity times 1/2 constant acceleration t squared. And velocity is a function of position. I have a acceleration equals v dv ds, and I do the integrals, and I end up with these three terms. Now, the important thing in all of this is that this applies to constant acceleration. And the assumption is that when I do these integrals, this one or this one or this one here, the AC is pulled out and it doesn't play a role. We're going to be studying kinetics and kinematics of motion. And in terms of the conclusions of this, speed is a magnitude, or is magnitude of velocity. Velocity has magnitude and direction. Acceleration has magnitude and directions. And we defined a set of relations for constant acceleration. And in particular, I want you to think about gravity as you go through this chapter and the rest of the course.